Now we can see the full model of fish, which incorporates the interaction and our extra source of fishing effort. So if we look at the model of fish, we can see that we still have elements from tank. We have our immigration of fish coming into our population of fish, and we have our emigration of fish. So if we ignore the interaction and the fishing effort for now, we can see that it's just tank model here in these brackets, one input, one output. The output is proportional to the population of fish. But now we have the interaction, which is an extra outflow from the storage of fish, and that's going to be proportional to the amount of fish we have, Q, and the fishing effort, F. Therefore the use or the catch of fish is K3QF. So we need to add that as an outflow from our tank model. So now full model for fish includes that extra third pathway. We should also note that the production of fish, or the landing of fish, the fish that we have on the boat ready to sell, is proportional to KPQF, and that does not become part of the differential equation for Q, because K3 is the actual catch, the removal of fish from the population. KPQF would be the amount of fish that we actually have on the boat ready to sell. So we could have lost quite a number of fish in the process, killed fish that stayed in the water, or brought fish on the boat that we don't sell, and those would be kind of the wasted fish, would equal K3QF minus KPQF. After determining the mathematics behind the fish model, which we can see here in the top, the next step is to perform the calibration, or determine what the K pathway coefficients are going to be. So here in orange, we can see that we've captured information about our fishing example. We know we have 10 metric tons of fish outside of our fishery that's supplying fish to us at a rate of 5 grams per meter square per day. And if we when we visited our fishery and took samples, we had 1,000 grams per square meter within the fishery. Under those conditions, we were losing 3 grams per square meter per day of fish to emigration naturally. And then we were taking 2 grams per square meter per day fish as catch. And in order to do that, we had to have 10 boats, and then we had to have our 1,000 grams per square meter of fish. So if you notice, we have 5 coming in and 3 plus 2 leaving. We have a situation where the inputs equal the outputs, or what's known as steady state, where the inputs equal the outputs, or the change in storage is 0 under this calibration. We also can note that our interaction, although we're catching 2 fish, taking those out of our fishery, we're only landing 1.5 of the fish. We've lost 0.5 gram. So it's not 100% efficient, it's only 75% efficient. 75% of 2 is 1.5. Notice that we have mass balance at our interaction as well. 2 equals 1.5 plus 0.5. So now what we want to do is we want to take our information in orange, our calibration values, use our equations, the terms of each of our pathways, and solve for the coefficient, because we know all the other information. We know E, and we know what K1E equals. It equals 5. So our calibration information about our pathway flow and our equation solve for K1 to determine what K1 is. So our flow here, J1 equals K1E, and that equals 5. So we could say J1 equals K1E. That's what's going on in this pathway. J1 equals K1E. We want to know K1, so let's solve for that. That means it equals J1 divided by E. We know J1, it's 5, and E is 10. We could substitute in 5 grams per square meter per day times 1 over E, which is 1 over 10 metric tons, and we would get a value of 0.5 grams per square meter day per metric ton of fish. We're going to leave it in these units because this makes it easier for us to interpret the meaning behind this. We're not going to cancel out units even though we know that we have mass in grams in the numerator and metric tons in the denominator. Next step would be to calibrate for K3. So again, we can say that this pathway is J3, it equals K3 QF. Solve for K3. We know everything on the right hand side of the equation. We know J3 is 2, and we know that Q is 1,000, and we know that F is 10. Put our F in there. We could substitute in 2 grams per square meter day times 1 over 1,000 is our Q, so that's grams square meters, and then 1 over our 10 boats. Solve, and we'll get 0.002. We can cancel out our grams, in this case, in our square meters, and we'll see that we have 0.02 per day per boat. And this is what K3 equals. Likewise, we can do for K2, J2 equals K2 Q. Solve for K2, J2 over Q. Substitute in our J2 is 3 grams square meter day. 1 over times 1 over Q, 1 square meter is 1,000 grams. Grams cancel out, square meters cancel out. We're left with K2 equals 0.003 per day. We left out a decimal place in our K3, so that should be 3 zeros and a 2. Now we're ready to move to the Excel spreadsheet. We have our calibration values, we have our equation, so let's go there next.